Hello everyone, how are you all? I hope you all are fine and safe. Well, again, welcome back to Quant Toffee, and I am Aman, just welcoming you all to a new amazing video. Okay, so as I promised in the last video to you all guys that I'm just going to bring a video on on the proof of this fantastic relation. The Dirichlet eta of s was equal to 1 minus 2 to the 1 minus s times the Riemann zeta of s. So yeah, that is what we are going to prove in this video, and it's not gonna take a lot of time. And yeah, let's begin the proof. But before that, this is going to have a look at some things like this, like the harmonic series. Harmonic series is the series as defined here that as infinite series that n goes from 1 to infinity of 1 over n, and basically this is Riemann zeta of 1, right? We will have a look at that also, don't worry about that. Or the Riemann zeta of z is represented as infinite series as n goes from 1 to infinity of 1 over n to the s. So when you replace s with I'm sorry, I yeah yeah that's fine. So yeah, when you replace z with 1, so you are going to have this harmonic series, and that is only the harmonic series. That series is known as the harmonic series, right? Okay. And next, if we care about the alternative harmonic series, so this is the alternative harmonic series, and again this is, well, if we talk about this one and this one, so these two are equal. When you expand them separately, so you are going to have this one series only. And guess what, this series is known as the Dirichlet eta function, right? Okay, so here it is, Dirichlet eta function that is equal to the infinite series as n goes from 1 to infinity of -1 to the n minus 1 over n to the s. Oh, I'm sorry, I just missed that this the Dirichlet eta function of 1, right? Be careful about that, because the Dirichlet eta of s, it should be s here, but it's 1, so it's the basically it's the Dirichlet eta of 1, right? Okay. And this is, oh, I'm sorry, this is the real Dirichlet eta function, right? And yeah, we are just going to use this thing to prove that this relation, right? But okay, but before that, let's just prove this, the eta of 1. Let's prove that the eta of 1 equals ln 2, right? And be careful that these two infinite series both are equal to each other, because when you expand them finally, so they ain't gonna just violate our infinite series, right? Okay, so now let's prove that down. Okay, so this theorem is proved using the infinite geometric series as follows. Okay, so we are just going to use the infinite geometric series. Let s equals the basic geometric infinite series, actually that is the infinite geometric series. Let's multiply x with s, so this is how it becomes. And yeah, so as we multiplied x with s here in order to get something like this, and now we are just going to use this thing like s minus x times s. So when you just have a look at this, the crazy part is when you subtract this one with this one, like if we talk about s minus s times x, so x minus x x square minus x square, x cube minus x cube, and this just goes up to infinity, and we're just left with 1. So it means that this equals 1, right? So when you take common s here, so 1 minus x equals 1, hence s comes out to be 1 over 1 minus x. And that's amazing. We have just proved a, a general infinite geometric series, and we use it in our daily life always. So yeah, this is how the proof of this looks like, and hence we say that this thing equal to each other, these two things are equals each other, right? Now we are going to integrating both sides with respect to x as we did here. So now just you can use the separate integration in all cases, and if we talk about the integral of this one, so it's ln of 1 minus x with a negative sign outside, right? Yeah, so here it is. You can do that the way here it's done. You can do that by that way also, but the basic way, yeah, you can guess it out. No, it's not difficult at all. And if we talk about, oh, I'm sorry, if we talk about this big part, so that is going to be x plus x squared over 2 plus x cubed over 3, and plus that keeps up to infinity, right? Okay. And now if we talk about this one, so we can write this as the infinite series as n goes from 1 to infinity of x to the n over n, right? So that was equal to negative of ln of 1 minus x. So ln of 1 minus x comes out to be negative of the infinite series as n goes from 1 to infinity of x to the n over n, right? And now we're just going to substitute x equals negative 1, right? I hope you can see that right over here. So now that is gonna become, when we talk about here, so when you talk about this part, so that's gonna be ln, oh, I'm sorry, ln of 1 minus, so when you plug x with minus, so that's gonna be, yeah, so when you plug x equals negative 1, so that's gonna be plus 1, so that's gonna be eventually ln of 2, and this infinite series becomes the infinite series as n goes from 1 to infinity of negative 1 to the n over n. And yeah, and there was a negative sign outside, so be careful. We can write this as in two ways, something like this one. When we consider that the negative 1 factor is in the numerator, so that's gonna be negative 1 to the n plus 1 over n, and the another one is the infinite sum as n goes from 1 to infinity of, we can consider that it's in the denominator, that's the negative factor is in the denominator, right? So that's gonna be negative 1 to the n minus 1 over n, right? Okay, so basically these two things are equal. So yeah, these two things are equal to each other as we discussed it earlier, right? So hence we can say after all this discussion that eta of 1, that is this infinite sum negative 1 to the n plus 1 over n, or the infinite sum of negative 1 to the n minus 1 over n, that comes out to be ln of 2. So this is the first part of our today's, first conclusion of our today's video. And now we are just going to move on to the proof that we are here for, right? Okay, so let me just erase all this stuff here. Yeah, so here comes the important part, and here is the Riemann zeta of s. So just be careful about the condition that here it is applied for, the real part of s should be greater than 1. And if we talk about the Dirichlet eta function, so this is here as we talked about it earlier, right? Okay, so basically, this is the relation that we are going to prove here, right? And this is the relation that I have used in the video that I'm posting, but actually I'm having some sort of problem in internet. That is why uh, I'm just having problem in posting that video. Okay, so now if we talk about the Riemann zeta of S minus the Dirichlet of S. So firstly, let's talk about the Riemann zeta of S. Here we are having a plenty of space, so we are just going to use this. Yeah, Riemann zeta of S was the sum as n goes from 1 to infinity of 1 over n to the S. And if we talk about the Dirichlet eta of S, so that is what the infinite series as n goes from 1 to infinity of negative 1 to the n minus 1 over n to the S. And if we talk about the zeta of S minus eta of S, so this is the infinite sum as n goes from 1 to infinity of 1 over n to the S minus the infinite sum as n goes from 1 to infinity of negative 1 to the n minus 1 over n to the S, right? And yeah, so here we did that. And if we expand these two things separately, so let's expand them. When you plug n equals 1 s sorry yeah n equals 1, so n 1 to the S minus that's gonna be 1 over 1 to the S plus 1 2 to the S, right? And that's gonna be, when you plug n equals 2, so that's gonna be negative 1 over 2 to the S, right? Am I going right? Oh, I'm sorry. I'm sorry. Did I do something mistake? Oh, yeah. I just forgot about this negative factor. So eventually that's gonna be positive. And if we talk about 1 over 3 to the S and then 3 minus 1, so that's gonna be negative of 1 over 3 to the S and plus 1 over, so actually we are only having two separate parts of the same terms of even like reciprocal, like what I'm talking about, this one, and eventually they are going to cancel them each other, right? Okay, so yeah, that is what we just here we noticed here. And if we talk about 4 to the S, so that's going to be positive 4 to the S, because eventually we are having a negative factor. And if we talk about this term, so this was negative 1 over 4 to the S. So to neutralize that, we are having negative, so they are going to be positive, and hence we are having positive. So basically this one and this one cancels out, these two combines, this one and this one cancels out, these two combines. So we are having that Riemann zeta of S minus Dirichlet eta of S comes out to be 1 over we can say 2 over 2 to the S plus 2 over 4 to the S plus 2 over 8 to the 8 to the S plus dot 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 to infinity. I'm sorry, I just forgot about, what, okay, let me just fix it. Yeah, so it's 6 to the S and plus dot 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 dot. Oh, let me just write down the next term, that is 2 over 8 to the S and dot 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 to infinity, right? Okay, so now what we did here is we can say that it's yeah, we can factor out 2 here, so that's gonna be the infinite sum as n goes from 1 to infinity of 1 over 2 to the 2n to the 2n to the S, right? So this is what we are having. And next what, okay, so now we can just do this 2 times the infinite sum as n goes from 1 to infinity of, we can write this as 2 to the S times n to the S. And we can write this as, well, since this term, this term is independent of n, so that's going to be factored out. So 2 to the S and the infinite sum as n goes from 1 to infinity of 1 over n to the S. And be careful that this is your zeta of s, right? So eventually we are having Riemann zeta of s minus eta of s equals 2 over 2 to the s times zeta of s. We can write this as 2 2 to the 1 minus s, right? We can write that as using the basic exponents exponentials. So we can write this as Riemann zeta of s minus 2 to the 1 minus s times Riemann zeta of s comes out to be eta of s. And hence we can say that after this factoring out the Riemann zeta of x from here, s from here, so that's gonna be 1 minus 2 to the 1 minus s times the Riemann zeta of s comes out to be the eta of s. Hence we can say that hence proved. Yeah, so yeah, that was kind of good and we did quite good things. And yeah, I just wanted to keep this video short because I know long videos are not made for my type of guys to upload on YouTube as a beginner here, but it's all right. uh, Thank you so much for watching this video, guys. If you got to learn something from my video, just make sure to subscribe, like and share, and just stay tuned for the next video. Thank you, goodbye, have a good day, goodbye.